Good morning and hello to everyone. Welcome back to my YouTube channel. I'm Dr. Hiya Poro. I'm an endocrinologist practicing at UAE. So today shall be continuing our class on endocrine changes in pregnancy. I shall be covering the part 2 of this chapter. This is chapter number 19 with Williams. So let's start. So today we will discuss placental hormone production. So let's begin with a question. Which of the following is not a source of cholesterol in the placenta? A. VLDL, B. HDL, C. LDL, or D. chylomicrons? Yes, the answer is D, that is chylomicrons. So we know that cholesterol is a very important source of steroid hormones, and there are a lot of steroid hormones which are produced in the pregnancy, also synthesized by the placenta. And for this, the placenta requires cholesterol, and this cholesterol is derived from VLDL, HDL, and LDL receptors, but not from the chylomicrons. Second question: which of the following enzymes is absent in the placenta? A. 3 beta hydroxysteroid dehydrogenase 1, B. 17 alpha hydroxylase, C. 17 beta hydroxysteroid dehydrogenase, or D. sulfatase. So, which of the following enzymes is absent in the placenta? Yes, the answer is B, that is 17 alpha hydroxylase. So, as we know, the placenta is a storehouse of, it is the manufacturing unit of a lot of hormones, and for this, it requires enzymes. But one enzyme is absent in the placenta, and that is known as a 17 alpha hydroxylase. And in the subsequent slides, we will come to know of what this enzyme is actually responsible for. Now, let us discuss the sex steroid production from the maternal, fetal, and placental unit. As we know, the sex steroid production in the adult ovary, it is a two-cell process that you already know. Now, what is this two-cell concept? So, this two-cell concept actually it comprises the two cells, that is the theca cells and the granulosa cells. And both these theca cells and granulosa cells, they have distinct roles in steroidogenesis. The steroid hormones which are produced by the adult ovary are progesterone, testosterone, and estrogens. Now, the theca cells, they are responsible for converting cholesterol into progesterone, testosterone, and other androgens. However, the theca cells, they lack an important enzyme, which is known as the aromatase, and they cannot convert androgens into estrogens. So the theca cells, they have got a deficiency. They lack the enzyme, which is known as the aromatase, and so they cannot convert androgens into estrogens. This deficiency is, however, overcome by the presence of granulosa cells. The granulosa cells they possess an abundance of aromatase, so the granulosa cells take up androgens from the theca cells and they rapidly convert these androgens into estrogens. So this two-cell interaction between theca cells and granulosa cells it is essential for estrogen production in the ovary. Now, how is steroid hormones produced during pregnancy? In pregnancy, the production of steroid hormones it becomes more complex, and it involves the maternal adrenal glands, the fetal adrenal glands, and the placenta. So these three components, that is the maternal adrenal glands, fetal adrenal glands, and the placenta, they interact among themselves to produce large amounts of progesterone and estrogens. So these hormones, that is progesterone and estrogen, are required for supporting and sustaining the pregnancy. The concept of the maternal fetal placental unit is very, very important to steroid production during pregnancy. Now, this unit, that is the maternal fetal placental unit, it is crucial for establishing the pregnancy, supporting the growth and development of the pregnancy, and also contributing to delivery. Now, let us discuss the overview of placental progesterone production. So, how does the placenta produce progesterone? So, as we know, the progesterone is the most important hormone in pregnancy. The progesterone is the hormone which supports and sustains the pregnancy. And placenta is like the theca cells in the ovary, it also produces progesterone, and placenta is actually the primary source of progesterone during the later part of the pregnancy. The placenta relies on maternal cholesterol because it has got low HMG coenzyme A activities. So the placenta itself cannot produce cholesterol because it does not have the coenzyme A activity which is required for cholesterol production. Cholesterol to the placenta is delivered via VLDL, LDL and HDL receptors present in the syncytotrophoblast. So this was the question that was asked. So cholesterol in the placenta is derived from VLDL, LDL, and HDL receptors present in the syncytotrophoblast. Now, how does the conversion process occur in the placenta? In the placenta, cholesterol is converted to pregnenolone by the enzyme 11-alpha hydroxylase. So, the first step for progesterone production is that cholesterol is converted to pregnenolone with the help of the enzyme 11-alpha hydroxylase. Pregnenolone is further converted to progesterone by 3-beta hydroxysteroid dehydrogenase. So, this enzyme is present in the placenta, and that is 3-beta hydroxysteroid dehydrogenase, which is responsible for the conversion of pregnenolone to progesterone. However, the placenta lacks 17-alpha hydroxylase, which is responsible for the conversion of progesterone to androgens. So, this question was asked in question number 2. The placenta lacks the enzyme 17-alpha hydroxylase, which is responsible for the conversion of progesterone to androgens. So this slide is very, very important. Cholesterol converted to pregnenolone with 11-alpha hydroxylase. Pregnenolone further converted to progesterone with 3-beta hydroxysteroid dehydrogenase. But the placenta lacks 17-alpha hydroxylase, so it is not responsible for the conversion of progesterone to androgens. Now, what is the role of placental progesterone? 90% of progesterone is released into the maternal circulation. Progesterone is vital for maintaining the uterine quiescence during pregnancies. Basically, it is the hormone which supports the pregnancy. It prevents preterm birth. Progesterone actually helps in preventing miscarriages and preterm birth. And progesterone also serves as a substrate for the fetal adrenal glucocorticoid and mineralocorticoid production. Now, what is the fetal contribution to estrogen production? The trophoblast, it cannot directly convert progesterone to estrogen due to the lack of the 17-alpha hydroxylase activity. So this pregnenolone, it enters the fetal compartment and is processed in the fetal adrenal cortex and liver. This process leads to the formation of dehydroepiandrosterone sulfate and eventually estriol, which is the major estrogen during pregnancy. So you might be asked, which is the major estrogen during pregnancy? So remember, the major estrogen during pregnancy is estriol and not estradiol. So remember that the trophoblast cannot directly convert progesterone into estrogen. Pregnenolone enters the fetal compartment. It is processed by the fetal adrenal cortex in the liver. This process leads to the formation of DHEAS and eventually estriol, which is the major estrogen during pregnancy. DHEAS is converted into 16-alpha hydroxy DHEAS in the fetal liver, which is then metabolized in the placenta to form estriol. Estriol is conjugated in the maternal liver and excreted in the urine. 90% of estriol in, just one second. Sorry for the interruption. 90% of estriol in the maternal circulation comes from the fetal precursors, serving as a surrogate of fetal well-being. So this estriol in the maternal circulation, the main precursor is the fetus, and this estriol is actually a surrogate of fetal well-being. So if the estriol level is low, this indicates that there is some problem with the fetus. Additional estrogen production pathways. DHEAS from both the fetus and the mother is taken up by the placenta and it is converted to estradiol through certain enzymes like sulfatase, 3-beta HSD1, 17-beta HSD, and aromatase, and it is also converted to estrone via similar pathways. There is another estrogen which is produced during pregnancy that is known as estetrol. Estetrol is a unique estrogen which is produced in pregnancy. It is produced by 15-alpha hydroxylation of 16-alpha DHEAS in the fetal adrenal and further enzymatic conversion in the placenta. So this estetrol is a very unique estrogen which is produced only during pregnancy. So to conclude, a placental hormone production is a very complex interaction involving the maternal and the fetal systems. The maternal fetal placental unit is essential for sustaining pregnancy, ensuring fetal well-being, and also contributing to hormonal balance throughout the gestation. So this is a figure that you will see in the Williams textbook of endocrinology. So you can see the maternal and the fetal compartment as well as the placental compartment. So we can see that the cholesterol is converted to pregnenolone and DHEAs in the maternal compartment. The cholesterol is then delivered to the placenta, and then it undergoes conversion from pregnenolone to progesterone. And this pregnenolone also enters the fetal compartment, and in the fetal adrenal cortex, it undergoes conversion to DHEA sulfate, and this DHEAs undergoes further conversion to form various types of estrogen like estetrol and estriol and estradiol as well. And the fetal liver also plays some role in the conversion of DHEAs to various byproducts of DHEAs. So this figure is very, very important. You will find this figure in the Williams textbook, so you should go through this figure. And the questions that may be asked in your entrance exams are like which enzyme is lacking in the placenta, which is the source of cholesterol in the placenta, then which is the major estrogen during pregnancy. So all these type of questions may be asked in your entrance exams as well as in your exit exams. Okay, now come to the protein hormones produced by the placenta. So till now we were discussing the steroid hormones produced by the placenta, but there are certain protein hormones also produced by the placenta. And the most important protein hormone that is produced by the placenta is the human chorionic gonadotropin, which is the hormone of pregnancy. So this human chorionic gonadotropin or HCG it is a glycoprotein. It is composed of two subunits, alpha and beta. Both the subunits are non-covalently linked by hydrophobic bonds. So this is important that they are non-covalently linked by hydrophobic bonds. And this HCG, it has got a lot of structural homology with other hormones such as LH, FSH, and TSH. The subunit, that is alpha subunit, is identical across all the glycoprotein hormones. So this alpha subunit is identical with LH, FSH, and TSH. The beta subunit is unique to HCG, and this beta subunit is responsible for its biological and immunological specificity. So now coming to the molecular details of HCG, the beta subunit, which is the primary, the primary subunit which is responsible for the unique biological and immunological properties of HCG. This beta subunit has got 145 amino acids, and there is 80% homology to the LH beta subunit. It contains additional 24 amino acids that enhance biological activity. It features two N-linked oligosaccharides and four O-linked oligosaccharide units. Now, how is the HCG synthesized? The genes, that is the alpha subunit gene, is located on chromosome number 6, and the beta subunit gene is also a cluster of 6 genes, which is located on chromosome number 19. So the alpha subunit gene, it is located on chromosome number 6, and the beta subunit gene, it is actually a cluster of several genes, and this cluster is located on chromosome number 19. The production sites are in the placenta, it is produced in the syncytiotrophoblasts. The syncytiotrophoblasts produce both free subunits as well as both free subunits of HCG as well as intact HCG. And after production, it undergoes post-translational modifications before the subunits combine. So the post-translational modification occur in the form of glycosylation. Now, what is the secretion pattern of HCG? So, HCG can be detected as early as 6 to 9 days after conception. So, HCG is a hormone which is very, very sensitive for pregnancy. It can be detected as early as 6 to 9 days after conception. So, we know all the pregnancy kits, that is the urine pregnancy test kit or the blood pregnancy test, all of these actually detect the hormone HCG. So, HCG is very, very sensitive. This urine pregnancy test kit can detect even small amounts of HCG, and is detected very early, that is around 6 to 9 days after conception. The peak levels of HCG is seen at 8 to 10 weeks after last menstrual period. So you may be asked, when is the peak level of HCG seen during pregnancy? So the peak levels of HCG are seen at 8 to 10 weeks after the last menstrual period. And after that, there is a plateau, and the nadir of HCG is seen at 18 weeks, and then it remains low, and values remain constant until delivery. And what is the variation of HCG production during pregnancy? In early pregnancy, more beta subunits are synthesized, whereas in the late pregnancy, more alpha subunits are synthesized. Now, what are the regulatory factors for HCG? There are certain stimulators and inhibitors for HCG. The stimulators for HCG are the GnRH hormone, which is synthesized in the placenta. It stimulates HCG production. Other stimulators for HCG are cyclic AMP, prostaglandins, epinephrine, epidermal growth factor, and insulin. So remember, the prime stimulator is the GnRH hormone, which is again synthesized in the placenta, and other stimulators are cyclic AMP, prostaglandins, epinephrine, epidermal growth factor, and insulin. The inhibitors of HCG production are transforming growth factor beta, progesterone, and inhibin. HCG can also regulate its own production. It has got a property which is known as autoregulation. HCG regulates its own production through cyclic AMP. Now, what are the physiological functions of HCG? HCG binds to the LH-HCG receptor, which is a G protein coupled receptor. The primary function of HCG is the rescue of the corpus luteum. So, as we know that after ovulation and fertilization, there's formation of a corpus luteum. This corpus luteum is very important for supporting the pregnancy during the early period before the placenta takes over. So this HCG is important to prevent the luteal regression. So HCG helps in maintaining the corpus luteum so that the corpus luteum can support the early pregnancy. The other functions are this HCG, as I discussed in the last class, it has got weak TSH and FSH activity. So it has got thyrotropic activities. It can cause stimulation of the thyroid gland to produce more thyroid hormones. This in turn can lead to suppression of the TSH. So most of the time, the TSH of the pregnant woman can be suppressed, and this suppression usually occurs in the first trimester because of increased HCG activity. And if the HCG levels are quite high, particularly during multiple pregnancies like twin pregnancies or triplet pregnancy, HCG levels are more. So this can even cause clinical thyrotoxicosis. Now, coming to the metabolism of HCG, HCG follows a bi-exponential clearance pattern. There is a fast half-life and a slow half-life. The fast half-life of HCG occurs within 6 hours, and the slow half-life of HCG is 36 hours. There is 22% of HCG is excreted via urine and it appears unchanged. Then there are certain degradation products of HCG, and these degradation products includes free subunits and fragments. Now, there is a type of HCG which is known as the nicked HCG. So, what is nicked HCG? We will discuss. There are various types of HCG. That is the intact HCG, which means the complete form of the hormone combining both the alpha and the beta subunits. Then there is the free beta HCG, means the beta subunit only, which circulates separately. And nicked HCG is a degraded or cleaved version of the HCG. The nicked HCG refers to the cleaved or nicked form of the beta subunit of the HCG. The enzymatic activity breaks down the intact HCG, resulting in this nicked variant. So it is actually a degradation product of the beta subunit of the HCG. Now, what is the clinical relevance of nicked HCG? The clinical relevance is that elevated nicked HCG may be linked to certain abnormal pregnancies like Down syndrome, and it can be combined with other markers in prenatal screening. Certain cancers of pregnancy, as we will discuss the trophoblastic diseases, this can also show elevated nicked HCG. Now, there are certain non-pregnancy sources of HCG production as well. So, what are the sources other than the placenta which can produce the HCG? So, this is the pituitary gland. It can also produce some amount of HCG, and other tissues like testis, brain, kidney, and liver. So, remember, you may be asked this question: what are the non-pregnancy sources of HCG production? Pituitary gland, testis, brain, kidney, and liver. The normal presence in non-pregnant individuals, HCG can be present, but not to that very high levels. And especially in postmenopausal women, we can see some amount of presence of HCG. So this is the secretion pattern of maternal HCG throughout a normal pregnancy. So as we can see, the HCG level rises during the early pregnancy, peaks at around 8 to 12 weeks, and then as the pregnancy progresses, it gradually comes down, reaches another level at around 18 to 20 weeks, and after that, a constant level is maintained throughout delivery. And these are the proposed pathways for metabolism of human chorionic gonadotropin. This alpha and beta subunits is the intact HCG. Then beta subunits can also circulate as an isolated subunit, and it undergoes further degradation to form, certain products, which is known as the nicked HCG. It's easy with NICT. And alpha subunit can also undergo, glycosylation to form the big alpha, which is the hyperglycosylated form of the alpha subunit, CTP fragment, carboxy terminal fragment. So all these are actually the various degradation products of HCG. Now, lastly, coming to certain cancers of pregnancy related to HCG. So let's discuss the gestational trophoblastic disease. The gestational trophoblastic disease includes three forms: the complete and the partial moles, complete and partial hydatidiform moles, choriocarcinoma, and placental site trophoblastic tumor. What is complete molar pregnancy? The complete molar pregnancy occurs in 1 to 2 per thousand pregnancies. So the pathology involves there is hyperplasia of the trophoblast, there is marked edema of the chorionic villi, and there is absence of fetal tissues. So in the pregnancy, you will not see fetal tissues or any fetal pole, but you will see that there is marked edema of the chorionic villi and there is trophoblastic hyperplasia. And what is partial molar pregnancy? In partial molar, unlike the complete molar, you will say focal trophoblastic hyperplasia. There is also villus swelling, but not as marked as the complete mole. Fetal tissues may be present, but there is also associated congenital malformations. And what is persistent trophoblastic disease? This complete mole, 20% of the cases develop persistent trophoblastic disease, and partial mole, around 2 to 4% develop persistent trophoblastic disease. This persistent disease can occur after normal pregnancy, spontaneous, or even induced abortion. Choriocarcinoma is the most aggressive form of persistent trophoblastic disease. Choriocarcinoma can lead to complications like local uterine diseases such as bleeding and uterine rupture, and it may even undergo metastasis to the liver, lungs, and brain. And placental site trophoblastic tumor is the rarest form of gestational trophoblastic disease. It is derived from the intermediate trophoblast, and it can present with vaginal bleeding or amenorrhea. Now, what are the diagnostic and prognostic markers of gestational trophoblastic disease? The best marker is HCG. So, HCG secretion is seen in all neoplasms except placental site trophoblastic tumor. HCG levels actually correlate with the tumor burden and the prognosis. HCG is used for diagnosing, monitoring the treatment response, and also follow up. Uh, Okay, there is something which is known as phantom HCG. Phantom HCG is really false positive HCG due to the presence of heterophilic antibodies, which is confirmed by negative urine pregnancy test. So it should not have come in this slide only, but yeah, this phantom HCG is a false positive HCG because of heterophilic antibodies. And here the pregnancy test is negative, but HCG, blood HCG level is positive because of the heterophilic antibodies. So for gestational trophoblastic disease, we will serially monitor HCG to provide diagnostic and prognostic information. And vaginal ultrasonography is also important for scanning, and it is also important for diagnosis and follow-up. Treatment of gestational trophoblastic disease, the primary approach is uterine dilatation and evacuation. We have to evacuate the entire tumor and whatever products of conception are left. And certain adjunctive treatment are also required, like chemotherapy options such as methotrexate or actinomycin D. Okay, so that was all, and we will continue with the next part in the next class. Thank you very much.